In the last lecture or last few lectures, our focus was on looking at how DFT can be used to do efficient processing of LTI systems, and we primarily looked at how DFT helps us do linear convolution in a fast fashion. We looked at fast Fourier transform in that regard also. That is just one aspect of the discrete Fourier transform. It helps us do faster computations. What discrete Fourier transform also helps us do is that it helps us find out what kind of frequencies exist in continuous time signals, or what is known as spectral analysis. And why spectral analysis is interesting? For example, let's say you're trying to look at, for example, why Wi-Fi signals are not working well in this region. What you can do is, for example, sample some RF bandwidth, for example, the bandwidth that the Wi-Fi signals transmit on, and you do their DFT, you try to figure out which frequencies are sort of interfering with each other, and you perhaps set your Wi-Fi to a different place. That's just a sort of a consumer product kind of application. There are, of course, many other applications of spectral analysis. You could be looking at a PCB circuit and trying to find out whether there is some spurious frequency, and for that you basically take your signal, sample it, do DFT analysis, look at which frequencies are present or not. You could be interested in radar signal processing. So you are transmitting some waveform from your radar, it hits a plane, it reflects back, and of course the way you figure out the location or how far away some airplane is by looking at the time it takes from the transmission of your waveform and receiving it back. So that gives you the delay, and from that you can say, okay, I know the speed at which my waveform is traveling, so I can figure out how far it is. But if you want to figure out how fast the plane is going, well, that's a spectral analysis question, because of the fact that the plane is moving, that's going to give rise to the Doppler shift in your signal. So you receive your signal back, and now if you can look at, okay, what's the new frequency of the signal that I transmitted, and you know your original frequency, you can figure out the gap between the two, you know the Doppler shift, and from that you can figure out what speed the plane was moving at. So those are just some of the examples, but spectral analysis in general just means that you are given a signal, and here we'll just focus on the one-dimensional case. You are given a signal and you just ask which frequencies are present in it, and the way you want to do that is using DFT. So that's where we have to understand then what are the sort of drawbacks, or what are the things that we have to be aware of when we do spectral analysis using the DFT. So the question in spectral analysis is, of course, that we are given some signal SC of t, and we want to find out which frequencies are present or at which amplitude in SC of t. We are not just interested in which frequencies are present, but we are also interested in, for example, their relative magnitude, how is one frequency bigger than the other one, and so forth. So effectively, we want to find out about the Fourier transform, the continuous time Fourier transform SC of j omega, but we won't be able to do that because real-world signals don't follow a particular analytic form. You can't just look at a signal and compute by hand what is the Fourier transform. You really need to bring this signal into a digital system and do some evaluation. But when you do that in a digital system, the first thing you are faced with is the effect of basically you can't look at everything. You have the digitization effect. But the hope is that we can still make some conclusion about SC of j omega using some interesting sort of analysis or understanding about what does the spectral analysis entail. Okay, so then if you want to do spectral analysis, we are given this continuous time signal. What is the first thing that we need to do? We'll sample it. We want to do analysis inside a digital system, we'll sample it. But we don't know anything about the signal. So can we just sample it as it is? When you don't know what is the first principle of sampling, when you don't know really whether your signal has a particular, for example, form, what is the first principle of sampling that you do? You put an anti-aliasing filter in front of that signal. Okay, so you have a hypothesis that the signal I'm interested in, it ranges from this bandwidth to that this frequency to that frequency. Based upon that, you design an appropriate anti-aliasing filter. So you will have an anti-aliasing filter. And the hope is that this anti-aliasing filter does not destroy any of the frequencies that you are really interested in. So you do anti-aliasing filter and you still get a continuous time signal. But after that, now you sample it. We'll assume that we are just going to assume an ideal one, and you sample it at some time t. And of course, this time t is related to the bandwidth that you are interested in interrogating. Okay? So if you're looking at a Wi-Fi, if you're looking at Wi-Fi signals, and you know, okay, these signals live in certain band, 2.4 gigahertz to whatever endpoint it is, that's what you are going to basically, you are going to receive from your antenna, these RF signals, but then you are going to filter them up to that frequency. Okay, and this T is really determined by that. Now after that, you get Xn. Okay. So we can now start. We have sampled our signal. We are now obtaining this. But if you want to do spectral analysis, your goal is you want to analyze that inside your computer or some other device. And that requires that you have a certain finite collection of samples. So if you sample, for example, your Wi-Fi signal, okay, the Wi-Fi signals are if you sample at 2.4 gigahertz frequency, the Wi-Fi signals just keep on coming. They are not stopping. The RF doesn't stop after a while. But inside your computer, you have to put a stop at some point. You say, okay, I am going to collect these many samples, and after that, I'm going to do their analysis. Those samples could correspond to 1 minute of data, 1 hour of data, 1 day of data, but eventually, you have to put a stop to it. So whether you sort of stop, in your view, whether you stop at the, like by breaking the connection to the continuous world, you can equivalently say you are effectively stopping by you are sampling your signal, and after the sampling, you are only retaining some of the samples. So we don't know, this Xn could be of infinite duration. And most likely it will be of infinite duration if you are talking about band-limited signal. Right? So if something is band-limited, it of course exists in time forever. Think of a cosine. Cosine, just one frequency, but of course it's going to exist forever. So this is going to be of infinite duration. And the first thing after you sample for spectral analysis is that you get your Xn. Okay? Whether you do that explicitly or not is a different thing, but you get your Xn, and you multiply it with a finite duration sequence, which is called a window. You multiply it with Wn, which is called a window, to get Vn, and then you compute its DFT to get the DFT coefficients Vk. So this thing of multiplying your signal with a finite duration sequence, this is called windowing. And the simplest form of windowing is that you actually collect your samples for a certain duration and then you stop collecting them. And that kind of a window, so if you say that I'm going to actually only look at xn for n equal to 0, 1, up to, let's say, n minus 1, that is equivalent to saying that I'm actually looking at Vn equal to xn times Wn, where Wn is nothing but 1 for n equal to 0, 1, up to n minus 1, and 0 otherwise. So if you multiply a finite duration sequence with an infinite duration sequence, you get back a finite duration sequence. And the easiest way to turn an infinite duration sequence into a finite duration sequence is just say, I'm going to throw out everything beyond, let's say, 1,000 samples or 2,000 samples. Well, that is equivalent to saying you are just multiplying your xn with a finite duration sequence, which is just all ones for 2,000 samples, and then it becomes 0. Okay? So this type of a window, this Wn, if you are just keeping all your samples and throwing away the rest, then actually you never do this explicit operation of multiplication with Wn. There is no need. We still retain that expression because sometimes you do want to multiply with something different than a rectangular window. So this is called a rectangular window. Okay. Again, to repeat myself, rectangular window is nothing but saying you keep all the samples up to, let's say, 1,000 or 2,000 samples and throw everything else out. That's what rectangular window means. Okay. So the goal in spectral analysis is to understand that how do these operations that we are doing affect our Vk, and once we obtain this Vk, these DFT coefficients of Vn, so what do these coefficients tell us about the Fourier transform of SC, so SC of j omega? Okay, that's the goal we are after. And in most cases, we are happy to assume that the anti-aliasing filter is sort of ideal, the continuous to discrete conversion is sort of ideal, but there is no way you can avoid the effect of windowing. No matter what system you're using, eventually you have to say, enough, I have to stop taking my samples. Okay? And that creates some artifacts that we should have a good understanding of for good spectral analysis. So that is the focus of our discussion for spectral analysis using the DFT. Okay, so let's look at the effects of what does this windowing operation itself do. So what does the windowing operation look like? We have V of n equal to W of n times X of n. And we are computing the Fourier transform, the DFT coefficients of V of n. Okay, so the DFT coefficients of Vn of n are, of course, the samples of the DTFT of Vn. So let's ask ourselves then, what is the effect of windowing on the DTFT of Xn? So what is the DTFT of Vn? We are multiplying two sequences. And let's call the Fourier DTFT of Wn as W e to the j omega. Similarly, let's call the DTFT of Xn as x of e to the j omega. Now, if we multiply two sequences in time, what is the effect of that on the frequencies? We get periodic convolution. Okay? Not the regular convolution, because DTFT is periodic. Okay? So we get the DTFT of Vn, which I am going to write by V of e to the j omega, that is equal to 1 over 2 pi minus pi to pi. So that's due to the periodicity. Instead of minus infinity to infinity, convolution, so x of e to the j theta, w of e to the j omega minus theta d theta. Right? So we are multiplying these sequences in frequencies. We are doing the periodic convolution of the DTFTs, and this means that V of e to the j omega is definitely not going to be equal to x of e to the j omega. The only way V of e to the j omega will be equal to x of e to the j omega will be when? If this thing was an impulse. If this thing was simply 2 pi delta of omega. If this was 2 pi delta omega, then V of e to the j omega will be equal to x of e to the j omega. But that cannot happen. Why? Because what is if I say that my window had a Fourier transform of impulse, then I must have a sequence which is 1 forever. So it can't be a finite duration sequence. So the moment I say that my Wn is finite duration, this is finite duration, the moment I say that, I am guaranteeing that windowing messes up the Fourier transform of my original signal. Okay? So our goal is, though, we want to make V of e to the j omega as close to x of e to the j omega. We can never make it equal. Okay? As close to x of e to the j omega as possible up to certain design specifications. Okay, so, and the reason is that if you make V of e to the j omega close to x of e to the j omega, then that is equivalent to, because remember, DFT is nothing but samples of DTFT. So if we could do that, if V of e to the j omega was roughly equal to x of e to the j omega, then this will mean that V of k is approximately equal to x of k, the DFT coefficients. And then we could translate back to what does that mean in terms of the continuous frequencies of SC. So let's look at then what is the effect of, first of all, this what is the effect of this windowing operation, which is effectively, what is the effect of this periodic convolution? Okay. So here is an example. You are given the original signal. You can assume, of course, you have to use an anti-aliasing filter which cuts off at pi by t because you are using sampling of t. So sampling period is equal to t. And these two, although the fact that you will have to have some finite roll-off, they sort of look the same, especially if you were, let's say, interested only in this part and you were to oversample, then you could say, oh, I am more or less really sampling the signal that I was interested in. Okay, so this is the Fourier transform of x of n, or x of t. Now, the next goal is, of course, that you are going to sample that. So what is sampling going to do? You are an expert on that. It's going to simply scale my frequency axis and scale the amplitude. Okay, so there will be a scaling of the amplitude here too. But what happens after that? So this is your xn's Fourier transform. Let's say you pick some finite duration window. Most finite duration windows will have, this is not the reality, we'll look at what windows typically have the Fourier transform, but most finite duration windows will have some sort of a wide hump around 0. They can't be an impulse. So they will have some sort of a hump around 0. And now you are going to periodically convolve this thing with this. Okay? And once you do the convolution, then you see that the convolution with this hump is going to smooth out your curve even further. So if you, for example, focus on this region and look here, that region is sort of gone, right, because of the smoothing effect of convolution, of this convolution with this function. Okay, so this is your v of e to the j omega, and then you compute samples of this thing. So you compute the DFT coefficients, which are samples of the v e to the j omega. And the goal is, let's start unraveling this and ask, what do these samples mean in relation to the original signal that we started with at the top? Okay, so we'll look at the specific effect of the windowing operation. We'll see what it does in terms of the two terms you will hear are spectral leakage and resolution. But before we do that, let's ask ourselves, if these imperfections did not exist, if we say that v of e to the j omega was approximately equal to x of e to the j omega, which is approximately equal to sc of, which is approximately equal to x of e to the j little omega over t, okay, because you are sampling that, which is approximately equal to sc of e to the j little omega over t. There should be a capital T here, 1 over t, sorry. If all these approximations were to hold, you did not really have imperfections due to aliasing, due to non-ideal sampling, due to windowing. So in that case, what would DFT tell us? Because that's important to be able to relate the DFT coefficients in that case, and then we'll put on top of that the imperfections. Okay? So we'll start off with that discussion first, and then we'll go on to the effects of windowing. So let's ask ourselves, what is the meaning of DFT coefficients in terms of their relationship to the continuous frequencies. Okay, so we know that V of k, the DFT coefficients, provide us with samples of the DDFT. So the first thing we know is V of k corresponds to samples of V of e to the j omega for omega k equal to 2 pi k over n. So we are just sampling the frequencies every 2 pi over n radians. Right? This means that omega k, so omega k equal to 0, omega k is 0, omega of 0, and then if k equal to n minus 1, that is simply 2 pi minus 2 pi over n. So omega k always belongs to 0 and 2 pi minus 2 pi over n. On the other hand, we are interested in finding out what is the relationship of this Vk to the continuous time frequencies. So we are interested in knowing about continuous frequencies. And for that, we need to be able to relate the DFT coefficients first to the discrete frequencies and then the discrete frequencies to the continuous frequencies. Now we know the relationship between continuous and discrete frequencies, but that relationship exists only for discrete frequencies between minus pi and pi. Okay, so we know when little omega belongs to minus pi to pi, okay, then that corresponds to capital omega in minus pi by t to pi by t. But of course, a discrete frequency at, let's say, 2 pi doesn't correspond to a continuous frequency at 2 pi over t. Right? We only get a frequency at 2 pi over 2 pi in the discrete world because of the periodicity of the discrete time Fourier transform. So the first thing we need to do is ask ourselves, what do these samples V of k, what do these samples teach us about the continuous frequencies? And if we want to do that, then we better be able to say something about discrete frequencies in this range. Okay. Well, doing that is easy. So the DFT, for example, if you look at this example, so this is minus pi, this is pi, and this is 2 pi. Okay. And this is, of course, periodically repeated all the time. Now, DFT samples this D, so this is DTFT. This is, let's call it V of e to the j omega. DFT is sampling this between 0 and 2 pi. So it samples here, 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 and then it goes up to 2 pi minus 2 pi over n. But we also know, because of the periodicity, that when it samples at this point, that is the same as the sample at this point. Right? So this sample is the same as this sample because of the periodicity. Similarly, this last sample is the same as this sample. Okay. So the relationship between the frequencies that DFT samples and the frequencies that we are interested in is rather simple. As long as the frequencies are between 0 and pi, they correspond to the frequencies 0 and pi, but the frequencies that are above pi, between pi and 2 pi, they simply correspond to we can subtract 2 pi from those frequencies to find out about v of e to the j omega at frequencies between minus pi and pi. Okay. So this means that actually dft v of k tells us about, of course, frequencies little omega k till I'm making it tilde to make differentiate it from the usual little omega k equal to 2 pi k over nt. So it tells us about 2 pi k over n for k between 0 and n by 2, because n by 2 index means that you are either up to pi or below pi. So this last index is, of course, either n by 2, or if it's exactly at pi, it will be exactly n by 2, right, for n even. At the same time, it also tells us about little omega tilde k equal to 2 pi k over n minus 2 pi for n by 2 less than k less than or equal to n minus 1. Okay. So we can say that even though DFT coefficients are originally samples of v of e to the j omega from omega equal to 0 to omega equals to 2 pi minus 2 pi over n, they also give us information about frequencies between minus pi and pi. The only thing is we have to make the right transformation. Okay, we have to take this later half of this DFT, this part of the DFT, we take this and put it at the start from minus pi to 0. So we just take this and move it. We move it to minus pi. Okay? Or we subtract 2 pi from all the frequencies. So that is the first step that we need to do in DFT. We need to be able to tell which indices correspond to which discrete frequencies, but we must be talking about discrete frequencies between minus pi to pi. And we have done that here. Okay. Now, once we have done that, then we can ask what does V of k tell us about continuous frequencies. And the answer, once we have the mapping, once we are looking at only discrete frequencies from minus pi to pi, then we know the mapping between continuous and discrete frequencies. The mapping is capital omega k is equal to omega tilde k divided by t. So it's just a scaling of the frequency axis. So this means if you want to ask, V of k tells us something, and something is in brackets because it is not exactly equal to the frequency information because of all the imperfections that we have, especially the windowing. But V of k tells us something about the continuous frequency capital omega k equal to 2 pi k over n t for all k's that are between 0 and n by 2. But the moment you go above n by 2 in the DFT index, you have to make sure you subtract 2 pi over t. So this and omega k equal to 2 pi over n t minus 2 pi over t for n by 2 less than k less than or equal to n minus 1. Okay. In particular, if let's say you have V0, that is telling you something about the frequency at 0 hertz. That is very simple. Okay. But V of n minus 1 is actually telling you about the negative frequency. And you obtain that by doing this subtraction of minus 2 pi over t. Okay. In particular, the DFT is effectively sampling. If you go through this relationship between continuous and discrete frequencies, then DFT-based spectral analysis is effectively sampling the continuous frequencies every 2 pi over nt radians per second. So the gap between two samples is 2 pi over n in discrete frequencies. In continuous frequencies, that is 2 pi over nt radians per second, or 1 over nt hertz. And that effectively tells us how many samples of DFT you need. If someone says, I want to be able to look at my frequencies every, let's say, 5 hertz, because you can't look at all the frequencies, but you say, if I look at every 5 hertz apart frequencies, that is good enough for me. Okay, so that tells you what is the amount of how many points of the DFT you need to take. How many points you need to take, that will be a function of what's the separation in frequencies you want and your sampling time. So if, for example, t is equal to 8 kilohertz, and let's say you are interested in samples every 5 hertz, then this means that you need n to be at least greater than or equal to 40,000. And every sample will correspond to a frequency at 2 pi over nt. Okay. And those samples will be 5 hertz apart. Now, as I said, this helps you translate this helps you do the translation between, okay, this is my DFT index. I have now computed a DFT. This is my DFT index. What will it mean in terms of continuous frequency? Now let's go back to the question that we talked about earlier. Let's assume that all the approximations hold. Let's assume that SC of j omega, you do anti-aliasing, but you do anti-aliasing, but you don't lose much information. So SC of j omega is equal to XC of j omega. Okay. So this approximation is due to anti-aliasing. Okay. Let's assume that that approximation is true. The next approximation is due to the sampling. Let's assume that that is also ideal sampling, which means that the relationship between the continuous and discrete frequencies is that you have x. So t is the relationship, the scaling of the amplitudes, xc e to the j capital omega t. Hopefully everyone still remembers their 4th chapter, scaling of axis and amplitude. So this is due to the continuous to discrete conversion. And let's assume that the effect of windowing is also negligible. So that is equal to xc is equal to v of e to the j omega. So that is equal to v of e to the j capital omega t. Okay. So if I am looking at then a sample at little omega k equal to 2 pi over either 2 pi k over n or 2 pi k over n minus 2 pi, right? Then if I want to find out what is my frequency, so if I want to say what is sc of j omega k, where omega k is as I defined earlier, okay? So this omega k is as we have defined here. If I make that transformation, then what it says is that sc of j omega k, I can say that is simply equal to t times v of k. Okay? You just take your DFT that you computed, multiply it with your sampling period, and you get a sense of what does the continuous frequency behave at that value. What does that continuous time Fourier transform look like at that value? Okay, so this is the transformation. Now you have to be careful about, as I said, definition of this capital omega k. So it often happens that people just say, oh, v of n minus 1 corresponds to 2 pi n minus 1 over n, and they just divide that by t and give a frequency that actually doesn't even exist between minus pi by t and pi by t. Okay? So if you make that transformation, then all you have to do is multiply your DFT coefficient with capital T. Why this capital T? Because of the amplitude scaling when you go from discrete world to continuous world. Right? As I said, I hope you guys still remember when you go from the continuous to the discrete world, there is scaling by 1 over t in amplitude and multiplication by t if you go the other way around. So this time we are going from the discrete world to the continuous world. Okay. So this is what is the meaning of the DFT-based spectral analysis. And that is half of the spectral analysis. If you understand this transformation between the DFT coefficients and what does it mean in terms of the continuous world, then half the spectral analysis is done. The other half corresponds to understanding that actually these approximations are not true, that this equality is actually a big approximation, okay? And that even though these anti-aliasing filter and the continuous to discrete conversion can be ideal, this approximation, which is due to windowing, has non-negligible effects. And you need to be able to understand what effects windowing create to be able to interpret whatever you are seeing on either your spectrum analyzer or on your MATLAB. Okay. So that is what we'll focus on in the remaining part of this lecture. And the best way to understand that is by taking the example of a signal which is nothing but a pure sinusoid. Okay? Because if you understand what windowing does to analysis of one sinusoid, then you can understand what windowing will do to, in general, the whole spectral analysis. So the example we consider is pure sinusoids. And now we are moving on to the effects of windowing. So we say that xc of t, we are going to make the approximation that that is exactly equal to sc of t. So no effects due to aliasing. and that is equal to A naught times cosine of omega naught of t plus perhaps some phase shift plus A1 of cosine of omega 1 of t plus theta 1. And these are sinusoids that exist from t equal to minus infinity to infinity. So you sample them and you get xn equal to A naught cosine of little omega naught t plus theta 0 plus A1 cosine of little omega 1 t plus theta 1, where this little omega naught, so this little omega naught is simply capital omega naught t, and this little omega 1 is simply equal to capital omega 1 t, the usual conversion. So when we sample our pure sinusoids, we have two sinusoids. When we sample them, we get back exactly two sinusoids in discrete time. But, sorry, these shouldn't be t, these should be n. So we get two pure sinusoids, but the n for them goes from minus infinity to infinity. And we can't do spectral analysis on an infinite duration sequence. So what we end up doing is we are going to window it by multiplying xn with some window wn, where wn can be rectangular window, which just means you throw out everything after n minus 1 samples, or it could be something else. So the only criterion right now will say is wn is equal to 0 for all n not in 0, 1 up to n minus 1. So it's a window of length n. Now, we already know, we talked about what is the v e to the j omega. That is simply equal to 1 over 2 pi minus pi to pi x of e to the j theta w of e to the j omega minus theta d theta. Now, what is x of e to the j omega? What is the Fourier transform of xn? That is very simple. That is just two impulses. So we get x of e to the j omega is going to be, if I especially look at just the amplitude of that, x of e to the j omega, what will that look like? That is simply going to look like between minus pi and pi, it will have an impulse at little omega 1, little omega naught, and another impulse at minus omega naught with a height of a by 2. Right? So that's just the Fourier transform of a cosine. Similarly, I will have another impulse at, so A0, this is A0, and I'll have another impulse of height A1 by 2 at minus omega 1, and another one of minus omega 1 plus omega 1 of height A1 by 2. So let's look at then what is going to happen when you do periodic convolution. Yeah. So this should be n does not belong to 0 up to 1, n minus 1. Okay. So we are now looking at periodic convolution of x with w. Now what does convolution do in the case of if our original signal just consists of impulses, the sort of general principle, even though it's periodic convolution, the general principle remains the same. We'll just get the Fourier transform of W shifted at the locations of these impulses. Okay. So because of that shifting, actually V of e to the j omega will consist of no impulses. So even though we were looking for pure sinusoids, and pure sinusoids mean pure impulses, we actually end up looking at a Fourier transform which has no impulses. And it can even get worse. So let's look at the case of, start with W of n equal to rectangular window, which means that you just keep the first n samples and throw out everything else. Okay? So rectangular window will work with n equal to 64, theta 0, theta 1 equal to 0, and we are going to assume that t is 1 over 10 kilohertz. And let's assume that the first cosine has a higher amplitude, whereas the second cosine has a little bit of it has an amplitude of 0.75. Okay. So then let's look at what does V of e to the j omega look like in that case. So if you remember, your rectangular window has an expression over for the dTft of a rectangular window is sine over sine. So this is the Fourier transform of your rectangular window, and its height is 64 because it's a 64 length, so n equal to 64, and it's going to repeat itself. That's why it's not a sinc. Sinc doesn't repeat itself. Now, when you do convolution, what you are going to see is this whole thing sort of getting shifted. There will, of course, be the effects of this periodic convolution and all that, where these ripples will go beyond pi. But more or less, you can think of this whole thing getting shifted to the locations of the impulses. So originally, we had an impulse here at this location, this location, this location, and this location. Instead of that, we get the Fourier transform of the window gets shifted to those locations, and then we add all of those up. So what is the effect that we are seeing? First of all, not only that we don't have these impulses, instead of impulses, we have these sort of thick lobes standing in their places, but also there's something else happening. You are now getting energy where there was no energy. You are getting frequency content where there was no frequency content. Okay, your signal consisted of just two pure sinusoids, but if you look at the Fourier transform here, everywhere you have some energy. It's not that you get these four humps and then it's plain zero afterward. So this effect, which is called spectral leakage, whenever you do windowing, whenever you do spectral analysis with windowing, you have this effect of spectral leakage, which is that energy from the signal is going to leak into other frequencies. Okay. So that is one effect. What is the effect of having these things replaced, having the impulses replaced by these humps? You don't see that effect in this picture because the two frequencies that you started with, so remember this frequency corresponds to 2 pi by 6 into 10 to the 4 radians per second. My t is 10 kilohertz. And this corresponds to 2 pi by 3 into 10 to the 4 radians per second. Right now you don't see an effect because the frequencies are far apart from each other. But let's bring them closer. If instead of those frequencies being, so instead of omega naught and omega 1 equal to what we had earlier, let's say omega naught is now 2 pi by 14 into 10 to the 4, and omega 1 is 2 pi by 15 into 10 to the 4. Now these humps are coming closer to each other. And if we were to bring them too close, what is going to happen? They will merge into one hump. They'll just merge into one big lobe instead of having two lobes. Right? So here again, you see this pronounced leakage. This is leakage. So now you bring them closer to each other, and all of a sudden they are beginning to merge with each other. You can still make out that there are two frequencies. So we have reduced the space between them even further. You can still make out there are two frequencies, but barely. And if I were to bring them any closer, then this is what you get. You have two frequencies in your signal, but because of windowing, it appears to you as if you had only one frequency. Okay? So this is the effect of the windowing, that different frequencies sort of get merged into one frequency. You can't really tell frequencies apart if they are very close to each other. If you look at this picture and someone asks you how many frequencies, forget about DFT or samples of this. DFT comes after this. You are going to sample this afterward. But if someone just shows you this picture and asks you how many frequencies your signal had, you have no way of knowing whether you had one frequency or two frequencies. And of course, there is this other effect of leakage. Okay? So because of the fact that your Fourier transform of your window had this sort of width, it prevents you from distinguishing between two frequencies that are closer to each other than the width of the Fourier transform of your window. At the same time, the spectral leakage arises because of these things in your Fourier transform. Okay? And these things have special names in the literature on spectral analysis and in the literature on filter design. So here your m plus 1 equals n. Okay. So this is the example where you have a length 8 window. This part is called the main lobe. And the distance between where your window hits zeros or gets very small, that part is called the main lobe width. If you want to distinguish between two frequencies, you better make sure that the frequencies are far away from each other in relation to the width of the main lobe of your window. Okay. And as we will see, this main lobe width is inversely proportional to the length of the window. So the bigger the window you have, which means what? That you have to process more samples. The bigger the window you have, the more samples you process, but the advantage of that is that the main lobe width shrinks. And if the main lobe width shrinks, then that means you can distinguish between closer frequencies. If your main lobe width is large, which corresponds to smaller window, you can't distinguish between closer frequencies. Now these smaller humps, they are called side lobes. The effect of side lobes is that they create energy in places where you did not have. And imagine if you had a frequency which had a height of, like, let's say 0.05, really small. Well, that frequency will get hidden in these side lobes. Okay. So whereas the width of the main lobe determines whether you can distinguish between frequencies which are relatively of the same size, they have the same amplitude. The side lobe height, not the width, the height of the side lobe. Okay. The height of the side lobe in relation to your main lobe height, that determines whether you can find small energy frequencies in your signal or not. So if you go back, for example, to this case, look here. Because of the leakage, you have now energy which is this high. If you had a frequency which was actually just this tiny bit impulse, if you had some frequency located somewhere here, you will of course get the Fourier transform of the window shifted to this location, but that Fourier transform will be so small that it will be sort of buried in this leakage effect. Okay. So there are two concepts that are happening when you do windowing. One is you have the spectral resolution, which is determined by the width. So that is determined by the width of the main lobe. And the other is leakage, which is determined by not the width, but the relative height of the side lobes in relation to the main lobe. Okay. Ideally, you want your main lobe width to be small. You want a really skinny main lobe. And at the same time, you want your side lobes to be low. And it turns out that these are competing design criteria. You can't simultaneously achieve them for a given length of the window. If you fix the length of the window, you have to sacrifice one for the other. If you want to achieve both in the right fashion, then the only way to do that is you have to increase the length of the window. So to reiterate, we want, number one, windows that have smaller main lobe width. And we want windows that have lower side lobes. But for a given n, for a given length of the window, these are competing goals. So the rectangular window is the best in terms of the main lobe width. For a given length of the window, the best thing to do, if you are really after distinguishing between frequencies which are close to each other, the best thing to do is use a rectangular window, which is effectively saying keep all your samples that you can process and throw away all the other samples. Don't mess with the sample that you have kept. And that is great for main lobe width. But at the same time, rectangular window has the worst side lobe height. So if you are after finding out, if you think that your signal has frequencies, the relative sort of magnitude of your different frequencies is very large. You have some really small frequencies. Those frequencies are going to get buried under the leakage effect if you use rectangular window. Okay. So because of that, people study different types of windows, have studied various ones. There are about very popular windows. One is called Bartlett or the triangular window, and we'll see them what they look like. So that window for a length n, it is equal to simply a triangle 2n over m. 0 is less than n is less than or equal to m by 2. The assumption is that m is even, of course, and 2 minus 2n over m for m by 2 is less than n is less than or equal to m. So this is simply going to look like a triangle. You have the Hahn window. They're all named after the people who proposed and analyzed them. So that is equal to 0.5 minus 0.5 cosine of 2 pi n over m for 0 between n and m and 0 otherwise. There is the Hamming window. That is equal to 0.54, very similar to Hahn with a slightly different, basically constants, upfront coefficients. The general principle that these windows are trying to follow is the following. The smoother your window goes to 0. So if you think of your rectangular window, your rectangular window is 0, all of a sudden it becomes 1, stays 1, all of a sudden it becomes 0. So windows that go to 0 smoothly tend to have lower side lobes. And that's why you are sort of seeing, if you look at all these windows, they are going to 0, not in an abrupt fashion like the rectangular window does, but rather they are going to 0 in a smooth fashion. Okay. There is a Blackman window, which is combination of two cosines, so 0.42 minus 0.45 cosine of 2 pi n over m plus 0.08 cosine of 4 pi n over m. And they all lead to, for a fixed length, okay, that's the thing to keep in mind. For a fixed n, they all lead to compromise between the main lobe width and the side lobe height. So here are different plots of the windows. What you are seeing is just the envelope. These are discrete time sequences, okay? But just to avoid sort of plotting that many stem plots, this figure is just showing you the envelopes of those discrete time sequences. So rectangular window is, of course, just this box. And the other ones, as you can see, go to 0 in a rather smooth fashion. Okay, and rectangular is the worst, that it goes abruptly to 0. And if you then compare, if you plot in dB scale, if you look at the side lobe and the main lobe width, so this is your main lobe width, this is the rectangular window, and the side lobes are only 13 dB below the main lobe, which is not, it may be good for some cases, but it's not that great. Okay, At the same time, it has a really small main lobe width. Now, on the other hand, if you come to Bartlett, for example, so this is Bartlett, or triangular, its main lobe width increases, but its side lobe now is much smaller than the rectangular, which was only at 13 dB below. Okay, you can push it even further by, this is Hahn. So you can push that even further, and you keep on going down. Hamming has an even wider one. This is its peak side lobe. Okay, you go even below 40 dBs. And Blackman is sort of like the king in terms of pushing down the side lobes, but it's the worst in terms of the main lobe width. So this is Hamming, and this is Blackman. Okay. And you can do the comparison between all these windows by, so if you focus on the first three, this is the table in chapter 7. If you focus on the second and the third column, they all give you this sense that rectangular has the best main lobe width. It's proportional to 4 pi over the length of the window. Okay, it's 4 pi over n, but it has the highest side lobe, which is minus 13 dB only below your main lobe. Okay, Bartlett, on the other hand, at minus 25, but the main lobe doubles. So you effectively, for the given value of the length, you effectively have reduced your spectral resolution by a factor of 2. If previously you could look apart frequencies that were, let's say, 1 kilohertz, now you can only do that which are apart 2 kilohertz. Hahn, so if you look at Bartlett, Hahn, and Hamming, if you focus on this, they actually all have roughly the same main lobe width, but different side lobes. So among these three, actually, there is no reason for you to use anything other than Hamming. Okay, so you should use Hamming. If you are not going to use the rectangular, then you should really be using Hamming at some level rather than either Bartlett or Hahn, because the peak side lobe height of Hamming is much smaller, but it has roughly the same main lobe width as the others. And Blackman, the main lobe increases by a factor of 3 compared to rectangular. So it's 12 pi over roughly the length of the window. On the other hand, the peak side lobe is 44 dBs lower than rectangular. Now we are on a dB scale, that's a big number. So we are 44 dBs below, but at the same time we are losing a factor of 3 main lobe width. And it all depends upon the design specification that you want to follow, depending upon which window you want to use. Okay. Now, all these windows give you a sense of how to pick one over the other, but what if you want something in between? You don't really want maybe like 12 pi over m, you are happy with 10 pi over m. Maybe you want a peak side lobe of, instead of minus 57, you're happy with something like minus 50. Those are the questions that someone might be interested in, and Kaiser was able to provide us with a very nice solution. It is called Kaiser window, but in reality it's not one window. It's a parameterized function, which is a function of two parameters. One basically settles down. One is figures out what is the relationship you want between the main lobe width and the side lobes, and the other determines the length. And in particular, if you sort of turn this knob of the Kaiser window, it helps you go from rectangular to Blackman and all in between. Okay? So you can actually achieve a point, any desired point. It tells you, okay, if you want this sort of main lobe width, you should maybe use these parameters. Okay, and then once you determine that, then it tells you, okay, use the other parameter if you want this side lobe peak. So Kaiser window is what will go next, and that effectively takes care of all the windows that we have done, and that will be pretty much the end of spectral analysis using a DFT. The main thing you have to be aware of for that is how to map the indices of DFT to the continuous world, and the second is what is the effect of windowing. If you are aware of those two things, then you should have no trouble doing spectral analysis using DFT.